This is part two of the weekly recap of the events, seminars, and other venues I attended at Stanford. I'm on a sabbatical, so what I'm doing every week, I give a recap of all the activities, partly, hopefully, for people to get inspired, and partly for my own record. So this is going to be just one event. I discuss one event because it's really interesting and it's fairly deep, and I read a bunch of papers surrounded by it. And the idea is sort of the geometry of data and the geometry of neural nets. So the fundamental idea is that data has geometries. What that means is, if you look at a tree, it certainly has a geometry. And if you look at a house, if you look at a highway, if you look at the ocean, and so on and so forth, there's geometries. And those geometries can be exploited in data analysis. Those geometries also have an impact on neural nets. The event I attended by a researcher, I might be butchering the name, SueYeon Chung. She is a statistical physics person that is now working in neuroscience. So this alone, I think, should show the interesting crossover here. We're going from data analysis and math towards biological physical systems. Neural nets, whether they are biological or digital, actually doesn't make such a big difference in terms of abstract analysis. So this is the interesting part. I also came across independently a conference that happened a couple of months ago. It's a conference about symmetry and robot learning. I got inspired by Wang, one of the researchers that I discussed yesterday. So in a nutshell, what's going on here is that when we look at data from a robotics perspective, we have to deal with physical geometries. Clearly, grasping an egg, holding a pen, or shaking somebody's hand. These are geometries that we humans understand implicitly. Walking down a path, skiing down a chute, surfing a wave. These are all geometries that we implicitly understand. Now, we humans also have an understanding of physics because we know when a wave's coming, whether it's most likely, usually we know, whether we're going to wipe out or not. So we have a sense also for forces, for angular momentum, and those sort of things. Robots are still not there yet. I'm going to discuss all of this. So the purpose of this episode is to discuss this particular event. I'm not going to draw any conclusions or anything like that. The events discussion part of my podcast really is a record-keeping endeavor. And if I can draw conclusions, I will, and sometimes I will just leave it out there and then hopefully later on come back to it. This is Nothing Wrong podcast. It's November 12th, 2023. This is Krim Telco. It's a Sunday. There's no update. We are up 88.3% for the year. The market is up 14.8%. We're outperforming by 73.5%. So SueYeon had a presentation at the neurology building at Stanford. So she is working in the neurology department. However, she herself is a statistical physics person. Statistical physics looks at data and is kind of data science applied to physics, if you will. Of course, it's a lot more than that in terms of math. It's not necessarily theoretical physics in the sense that you're not trying to do what Dirac did, according to Richard Feynman, which is invent a formula and then interpret it. You're looking at data and you're trying to make sense from the data analysis about physical processes. So one application would be in cosmology, where actually geometry plays a role. So you look at, for example, the formation of stars, the formation of galaxies, and you try to understand from what we see today, what is the signal in the noise, and you go from there. Just as a tangent here, Ali Jalal is another researcher that I attended his presentation. I'm going to discuss it tangentially here. Maybe I'll do a formal part 3 where I talk about other events that I'm going to discuss. So it's going to be a part 3 here. This is part 2. But just tangentially, he was talking about compressed data analysis. What he was trying to do is find structures that in a sense, reconstruct an image with very little data. So this is definitely along the lines of what SueYeon is trying to do. So let me go step by step. First, let's talk about SueYeon. Then let's talk about a paper by Qualcomm Research that I came across that really captures well what geometric data actually means, geometric algebra applied to machine learning, and then I'm going to talk about Ajil Jalal also. So what SueYeon is trying to do is she's trying to answer the question, can we look at the geometry of data? So can we find geometric parameters that then can be captured by models and used for inference? Now, she herself is not going that far. That would be Qualcomm Research. What she's trying to do is she's saying that the geometry of data, that input, has an impact on the geometry of the neural network that is analyzing the data. So this is sort of the plasticity of the human brain allows that to happen. So we have neurons that form specifically according to the input signals. So the way I understand it is if you go to a rock concert, your neurons will form in a different way than if you go to a lecture about Kant. And the input defines the structure of the neural net. So the neural net, of course, let's say the human brain, there are certain things which are invariant, right? I mean, the brain's not going to turn into gas or something like that. So certain things are invariant, but the actual structure, the manifold, if you will, so the geometric structure of the neurons can change based on the input signal. This is the main idea here. I tried to read some of her papers and I wasn't able to dig deeper and understand what the actual application is. So that's why I'm jumping over now to the Qualcomm Research. Cohen is the lead there. He is a PhD from the University of Amsterdam, and he is a specialist in geometric algebra or geometric convolutional neural networks. So what that means is that you try to use symmetry as a tool to analyze data. So if I look at a tree, I don't have to understand every particular, let's say if I do a pixel analysis of a tree. So if I try to understand what is a tree, so I do image recognition, I can infer from a few pixels and using geometry or just my understanding of the symmetries of a tree. So the width. So if I have an understanding of the width of the tree and roughly the shape of the stump, I can understand roughly how the tree is going to look with very, very little data input. And I'm not surprised that Cohen's company that he co-founded with his professor at Amsterdam was bought by Qualcomm, because Qualcomm is incorporating this analysis into Snapdragon, which is a neural net enabled chip for mobile phones, right? So you have this problem of little input and compute per you're trying to optimize compute per watt. Now, what you're trying to optimize here is not necessarily compute per watt through hardware. You're trying to optimize inference per watt. So can I just really quickly draw inference from very little data? That's why this is related to the Ajil Jalal. I'm sorry if I'm butchering the name. I'll put all these papers and names in the show notes. But when we're talking about compressed data and reconstruction. Now, Jalal's paper is on a different frontier completely in terms of, from an engineering perspective. But the fundamental idea is similar. So Jalal's ideas, they come more from the sort of eigenvector or principal component analysis type field. So I would say it's more in that field. So you're looking at, okay, what are the principal structures of the data, and then can we reconstruct what's the minimal amount of data I need to reconstruct a picture? And that's not often that's not a quantity question, but it's more of a quality question. So if I have certain areas of data, Jalal's using MRI as an example. So if I scan the brain, I can use, I need very little data to reconstruct the brain. Now, what he was doing also, he was talking about the distribution of the input signal, and this is partly where my understanding of the math kind of, it doesn't work anymore. But you can see this is also, related to Ding Zhao, the CMU researcher that I discussed yesterday, task-specific learning, right? So it all goes back to, okay, look, let's understand what the data is that we need to learn a certain task or to learn a certain picture. It's not about quantity, it's about quality. So this is all research going in the same direction, but I don't want to lose track here. So let me just stay now with Taco Cohen. So what Taco Cohen is doing in a paper that was presented at the Symmetries Robotic Conference in Korea this year, he talks about a geometric transformer. So this is very, very concrete. You look at parameters that can be expressed in sort of geometric algebraic form, and those parameters, they are the tokens, and they can be learned, and that this model can be used for object recognition, object grasping. That's the idea. I'm not going to go deeper here because my understanding of the technicalities is limited. But what I really want to take away here is, and this is now a takeaway for the business, and let's not forget we're a hedge fund, we're investing in real-world AI. So why are we interested in robotics? Why is this paper in particular drawing our attention? Because we believe that the humanoid robot by Tesla is not just a pet project, but it is the attempt to solve for depth and dexterity through transfer learning from the FSD and bootstrap a robot so that people can learn from that, or other robots can learn from a robot. So that's the idea. I think this is a lot more profound than it might sound. I'm not sure I'm able to convey this, and I'm going to write a white paper about this soon, because it's really profound. So the idea is that we have certain priors that need to be solved, such as depth, such as how to analyze an object from a geometric perspective, and then of course also physics and from a touch material science perspective. But one thing that I've noticed in the conversations with the researchers is they're very, very focused on trying to solve one-dimensional problems. So it's let's solve the geometry problem, then let's solve the physics problem. Another question that comes up, of course, is where does omniverse stand here? Where is that part of the equation, meaning what NVIDIA is trying to do with simulation? But overall, again, I think what Tesla's doing here is incredibly profound. These types of papers, so the geometric transformer, the idea of data inputs, the geometry of data, forming also the geometry of neural nets. We have the inductive bias concept, and inductive bias is just that the model itself already has a bias. So for example, if you use a ReLU or a softmax or those types of elimination functions, you have an inductive bias to certain types of data that will be expressed more than other types of data. So you have to think about that too. And I think this opens up a whole plethora of ideas and problems and possible solutions towards the problem of real-world AI. This is, let's always keep sort of the compass is towards real-world AI, which is an embodied intelligence that moves around in nature, understands nature, understands the geometry of data, so it can grasp things, move around things with as little compute per watt as necessary to execute the task. This is the North Star. And works like the Qualcomm research work really are I think pretty interesting in that context, and we should take this very seriously. And it's very interesting to see how different companies are approaching this and how they all have their own, of course, North Star. Qualcomm needs to minimize the compute per watt as much as Tesla needs to minimize. They come from different angles. Qualcomm is a cell phone chips provider. Tesla wants to build a robot, but they have both the same problem. Although Qualcomm is solving the inference problem, not necessarily the compute problem. Of course, they're also in the compute problem business. They are making the chip. So they're trying to do both. And I think Tesla also has to try to innovate on the model side as much as they need to innovate on the hardware side. They've done that with an acquisition, I think, about 2 years ago, where they looked at a company very similar to Taco Cohen's company, where data structures can be used as an inductive bias for analysis. So what's the conclusion here? The conclusion is that it's worth understanding data structures, geometries of data. They have an impact on the networks, the neural nets. The neural nets, literally in the form of human brains, form based on the stimuli that come from the outside, and we can have the same analogy in digital nets. We have the inductive bias concept. This is incredibly important. That's where the model itself. So we can, models aren't neutral, of course. I mean that might sound obvious to researchers, but it does matter what kind of architecture you use because you have an inductive bias, and based on the problem that you're trying to solve, it's worth thinking about what kind of inductive bias you should use. Inductive bias can be a positive thing in a sense. That's what Cohen et al. Try to do with their geometric transformer, where they're actually trying to use symmetries as a tool to reduce the amount of data necessary to do inference. Of course, inductive bias can also be understood sort of on the negative side, that you miss information. But overall, it's a concept that's worth thinking about it. And I think SueYeon's presentation it's one of those beautiful examples that really opens up a whole plethora of ideas, of thoughts, of venues to go and do research. And that's what the beauty of a sabbatical. Thank you.